I see a lot of familiar faces. So, hello, friends. Some new faces. Thank you for joining us. So we have little time and a lot of stuff to share. So I would like to engage you as much as possible. That's my style. How many security experts we have in this room? Raise your hand. So you know what's wrong in this picture. Come on, don't be shy. What's wrong in this picture? Security experts and you don't know what's wrong in this picture? Why this picture is in a security deck? Why? You should know. Yeah. So let me give you a little help. That's what's wrong. If you go back to the other one, you cannot even see it, okay? So people really don't know what this is. Okay, so here is the whole story. That's what it is. So whether it's true or not, we don't know. Some people think it is, and the point is, how can you spot something that small on a board that supposedly ended up in Fortune 1000 companies? You cannot. How can you spot something wrong in an SOC? Some few extra gates. That's an order of magnitude bigger problem. But we have the solution, right? And it's called TPM. Everyone knows it. What are the security aspects? Oh, they're coming in right now. TPM is the solution to everything, right? Oops. No, really? What's wrong there? Now we have a solution for everything, right? Oops. Not really. We all love FreeRTOS. It's open source, so it's secure, right? Everyone can look into it, right? There's some problem there as well. And I love FreeRTOS. I love all the things I just showed. By no means I intend to diminish the value of them. But my point is, why is this picture in my deck? What's wrong with that picture? Because this is a new level of challenge you are facing as an industry. These gazillion little things are getting connected to physical entities, to our own bodies, are part of our lives. This is not virtual. This is not cyber anything. This is as real as it gets. And so we don't want to get people's minds hacked by a RISC-V processors, right? So now let's start the real presentation. This was a little bit more about an opener. Traditional computing, as we learn in school, is done in this way. Data center, not data center, mobile or not. This is what it is. You write code, some magic tools put all things together, and in the end you end up with something like this, which is there's some data, there is some code, and every single byte of instruction can access every single byte of your data. There's no escape really from that. Compiler links put everything together. These are what we call binaries. They end up somewhere in some place where they can be executed. And these blocks communicate through shared memory, where it's a stack, it's a heap, whether it is shared or not, but that's what it is in the end. So one faulty, malicious, whether it's intentional or not instruction, can really take down the whole system, which is the safety aspect. And I know what you think, Cesare, but you didn't take the class where they taught MMUs. It takes 17 million lines of code of Linux kernel to run an MMU. So do we really believe that's what we are telling the world, that you put 17 million lines of anything on top of something and that's secure? So no one makes all the software these days, byte one to buy whatever, right? We have third parties, we have dependencies. Some are open source, some are not. Some are black boxes of executables, drivers for, trust me, it's going to work at Wi-Fi because it's proprietary, it's non-free, even in Linux, and so forth. The other skeleton we have in the closet is that the complexity of some of the security technologies, it just simply makes them impossible to be used. And I don't want to name vendors or technologies, but you know what I'm talking about, right? Not even Qualcomm can get Snapdragon to work still now, and Android phones can be decrypted. That's the sad reality. It's just too complex. So I did a little bit of an exercise coming here. So you can do the same. This is vanilla out of Linux repo. And so that's what it is, 17 million lines of code. And you just run a bit of math, do your search. How many bugs per lines of code? So let me be very conservative. And according to some, I guess it's NASA or some aerospace, 1 out of 10 a la minus 4. That's pretty solid code. But if you run the numbers, that's still 1,700 accidents waiting to happen in every single Linux kernel that's running out there. And I love Linux, I run Linux, we only run Linux, okay? But that's what it is. So there must be a better solution. And so here is what we think is a better approach to this. Instead of going vertical, and say, oh, my lower level of the stack, the BIOS, and then I have the drivers, and then I build the OS, and there's the kernel, and then brings up user mode. Something goes wrong down there, the whole thing comes down. Perhaps it's time to look for something which is parallel, horizontal. So that if something goes wrong and will go wrong, stays where it is wrong. This is the basic concept of security through separation. People in security know this well. So sometimes I hear this is Dockers for at the silicon level. Fine, it's okay. It's the concept of virtualization, separation, containerization, call it however you want. If you can do something like this and you can enable, without sharing any kind of resources, these systems, you really have a way more robust system. Everyone in security knows 100% doesn't exist. People with resources, time, money, and nation government, nation states behind them will figure out ways to break things. But this makes things way more sound, okay, sounder. Okay, so let's get into a little bit of what RISC-V offer has. I was in a panel with the media just a few minutes ago, and they asked, so what's so special about RISC-V? I don't know if it's special. I can tell you because I know very well, that's what we do, what's in there. And so basically you have 3 building blocks. I'm trying to be a little bit generic here, but 3 building blocks that you get out of the box, in every core, basically. Every vendor, if it is this ISA, that's what you get. One is privilege levels. How many privilege levels are in RISC-V? There are 4 in the specs, but only 3 ever considered. We'll see what happened to the H mode, okay, hypervisor. But as of today, there is plenty for creating some separation. These are the rings, if you look at the rings. Right? There are 3 rings. Now, one is always there, that's M, otherwise it's not an ISA, a RISC-V ISA. And then you have typically M, which is intended for embedded that doesn't have an MMU, or you have S, supervisor, for something that's supposed to run Linux. But I see more and more, we work with actual commercial implementations. So our demos are downstairs in 3 different booths, 3 different companies. So this is as real as it gets. I see more and more all of these, the 3 rings together, because there's definitely a realization that the MMU alone cannot really save the world, but you cannot just do the safe zone, whatever you want to put the name there. You have to. Okay. So what else we have? Well, we have this PMA, PMP, and physical memory protection and company. So this is hardware enforced. There's nothing to do with caches, so you don't run into any kind of cache issue. If the core does a load store or tries to fetch anything, it has to comply with policies. Policies are kind of granular, so we have a kind of interesting combination. If there's flash, if there's RAM, if you are hitting some which is memory mapped and it's an I/O, perhaps you want to read the real-time clock. There's no harm in reading what time it is. Well, to reset it might have an implication, an impact on the system, so you can get at this level. You can overlap these ranges, and this is good if you have a model of consumer and producer, where the consumer cannot really affect the producer, or you can keep them just completely separated. Now, for people who are really technical, and I see a few in the room, you know who I'm talking about, it gets really a little bit more into the details. So the ISA is well designed. This is really good stuff. And so there's a lot of flexibility. So you have options of top of range or naturally aligned power of 2. Who knows what's naturally aligned power of 2? Yeah, so get it right. Otherwise, your system is not going to be secure. So just to have these pieces without really understanding what they do and how to put them together, you are not going to get security. And you will never figure out until someone breaks in. Keep this in the back of your mind. The trust execution environment, or whatever name you want to put there, TE is from global platform, seems to be kind of understood, but ARM with trust on these kind of things, right, are there to enable all of these components. Just something for you to think about. This is at the core level. All I said happens at the core level. Anything happens outside the core, what do you do? We'll see in a minute, okay? So this is the 3rd piece that you can have out of the box. You don't need to pay anything. It's already there, right? Which is the user mode interrupt, or N extensions. It's one of these placeholders we have in the specs. It's a great thing to have, but it's not available yet. But wait, there is a way eventually to get trap and emulation to achieve the same. Who knows what is user mode interrupts, by the way? Okay, so here is the story. You create all of this separation, you have all of these rings, and then an interrupt comes in. The processor jumps at the highest possible level of privilege and executes and breaks everything. You don't want that to happen. You have PMPs, put together the PMPs. You get an exception, the system breaks, because you don't know what you're doing in the end, right? Linux is not much different in the sense that everything goes up to the kernel, unless you do user mode interrupt, but that's a different story, okay? The outer ring, which is the M mode, so-called in our jargon, is what eventually delegates, and hardware is supposed to transfer control. It's great, makes a lot of sense. I haven't found an implementation yet of anything like this. And it's optional, as many of these pieces, okay? How do we put all things together? And so I try to, that's what I usually hear. So it's like Docker at the chip level. That's the kind of concept, right? So that's what multi-zone trust execution environment is about. If you're familiar with trust zone of ARM, this is an extension to multiple execution domains. They are all equally secure, and you can have as many as you want. There's no need to add hardware. No additional cores, no additional nothing. It's built into the specs itself. Unlimited number of equally secure zones, where you also get this policy enforcement. It's enforced by the core, so it's as solid as it can be. You cannot break that. But it's software enabled, which means that you can easily define these policies, and you can change them when you flash the system. Once it's flashed, it's signed, you don't change them. Interesting for people who know about fencing and all the conversation around out of order. Where we are as an industry, you either throw away all the goodies that come in through out of order, and you get fencing, security. That's Intel way to patch things. But then you really get a hit in terms of performance. That's what out of order is there in the first place, right? Or you go with not out of order, you go in order, but then you don't get that benefit of speed. With fencing and these kind of environments, if you put them together, what you can do is to have some zones that rely on fencing. And so you fence in or out or both when you're executing some entity, whatever is the functional way you break them down, which is safety critical. For the ones that are not that important in terms of safety, you can go faster. This can be done just by defining the system again, okay? We had the formal verification. Just to give you a sense, the multi-zone from RISC-V is 2 kilobytes. 2 kilobytes of handwritten, hand-picked assembly code. A nightmare for whoever writes it, because this is RISC, so you really don't have many choices of sophisticated instructions, but you get as small, as secure, and as verifiable as possible. Less than 1% of CPU, in fact, is way less. We have demos going downstairs if you want to check them out, and we have stats that run in real time. It's 100 cycles, basically, given or taken. It's nothing really on today's processor. And as I said, on the 32 bits is 1 kilobyte, on the 64 is 2 kilobytes. That's the only requirement. Interesting enough, if you're familiar with traditional trust execution environments, and we have Brandon here from Embedded Computing, who has some strong opinions. He's somewhere there, you will find him. If you need to change your code to get the benefits of this security infrastructure, then it's not going to happen, basically, right? So what you can do with this kind of architecture is that you can drop in your ELF. You can drop in your hex. If you have an executable, you drop it in, it will work. How we do the magic? Happy to explain some of the details later, because we only have 5 minutes left. And it's built from ground up for RISC-V. You can build it, we did it. You can go on GitHub and just get it. It's open source under Apache 2. And as I said, it's completely based on standard RISC-V extension. No need to get extra cores, extra IP, extra this, extra that. Fully integrated with Eclipse, fully integrated with, if you want to go with GDB, that's fine. So whatever it is, yeah, you use. Okay, so here is the big picture. So how do you design a secure system with RISC-V if you rely on this kind of architecture? There's no shared memory. There's no stack where you can put a call or expect something to return, because you can not do anything bad to that stack. There's no stack shared. There's no buffers. So the way you do is that each of these zones actually implement your choice, we don't have any preference for that, of security functionality. So whether you have, I don't know, Wolf SSL, crypto libraries, or you want to have intrinsic ID as a member of RISC-V, PAF, whatever. They are separated in zones. The operating system itself is in a zone, which is in this chart, the first one on the left. We have a project going on at the university in Europe where they actually put FreeRTOS in a zone. That's great. We like it. The next step, by the way, is to have just Linux running there as well. You can have a multiple of them, but that doesn't really make a lot of sense. What you want to have is your core security components, keep them separated, or safety critical to that extent. The bottom, the yellow part, is what keeps the separation going and allows for communications. People who try to create separation in systems, as I did starting a few years ago, first time I got it, I say, great, these things are really separated. And in fact, I can do nothing of the system because they cannot communicate. oh gosh, what do I do now? You need some sort of, in Linux this would be IPC or pipes, whatever you want to have, some way of communication which is enforced by the hardware itself. So this is out of the box, it's pre-certified. And as I said, it's open standard, the API is on GitHub. Anyone who wants to add and help us, feel free to do it. We are looking for contributors as well. Let me show you how it works from a developer perspective. What you see on the left is all the complexity you will ever get exposed. So who doesn't know about NAPOT? Natural line power of 2. Yeah, you know, right? People who don't know what are PMPs or this kind of, that's all the complexity you need to be exposed. And you don't change your code. You write in a flat file what are the boundaries of your memory map resources in your zones. So every zone, this is a real case examples that we have downstairs running. So this is as real as it gets. We have 3 zones in this case. For each zone, you define RAM, you define flash, whatever is where you run it in cache or not, and memory mapped resources, peripherals, UART, GPIOs, whatever you are using. You can overlap them, and you can eventually add security policies there, read, write, and so forth. In the first one, we also have fencing activated, which means that the first one, which is exposed to attack, it's a terminal, is the one where we fence in and fence out. So anything that is in any state of the processor gets just cleaned up. But we don't incur into performance hit in the other zones. You provide your zones already pre-compiled and pre-assembled, linked, whatever you want to do. We show a demo where you actually get the Sci-5 demo, the hello world that blinks the LEDs. We just get it and just drop it in the system. It just works like that. And the demo is designed to work in M mode, but it just works fine in an environment which is now secured and isolated. We do this through trap and emulation, but there are some specific things that also we added to that. And so then there is this loader. This is a signed secure boot loader, otherwise it would not work, that comes in. And this configurator utility, just bring all the things together, packs them, sign them, and you have your X image. The demos that we are showing takes 200 milliseconds, by the way, to go through the whole process. So it's absolutely transparent. So this is what we just posted under Apache. If you don't want to do the hard way, you want to go the easy way, there is an API here. This is a C API, but it's just an exception handling mechanism, so you can just go with assembly if you want and just provide the same information. Very basic thing, send, receive messages, which is the equivalent of placing a call on the stack or getting a value in return. Then you have a little bit more about the scheduler itself. So if you want to yield, people familiar with free real-time operating system knows what I'm talking about. Otherwise, the scheduler is preemptive. You set the tick, we set 10 milliseconds. After 10 milliseconds, the clock ticks and the word moves on with the next one. And then you have a bunch there of examples of what would be otherwise protected mode instructions that are just handled transparently by the system. People who are familiar with this would know what they are, but basically these are outer ring, the more secure ring instructions that in this case are just read-only. So there's no harm basically in knowing what ISA you are running, just to give an example of what time it is. And this is all the complexity you get exposed, which is really no complexity at all. If you have exception handlers for interrupts, so PMP has nothing to do with interrupts. So people who think they read a piece of paper and know what's PMP, they think they secure a system. Well, it's a good start, then you realize what it takes. So you need to be able to process interrupts. Interrupts are a bad animal because you want to have not just re-entrant, but also preemptible interrupts. You want to preempt an interrupt and execution interrupt. You want to do this across domains. It's a good exercise, okay? So it takes a lot of effort. Once everything is encapsulated here, the only thing you do is in that attribute, when you define the handler, you say this handler is an interrupt user mode. This is already in the new compiler. You don't need to change anything or hack anything. It's already there. It just works. The second one is an example of you communicate across zone. It sends a message to zone number 1, and the message is whatever you put in that stream of bytes, depending on how you design the system. What we have done with other universities was to actually get to projects where they wrap traditional APIs into messages, which is the most natural way to go. But you can get creative with that. And the last one is an example of how you register a handler to the system, which is, as you would expect, you just pass the name of the function, the pointer, and what interrupt is supposed to be mapped to that zone. Again, you don't want every zone to be able to process every interrupt. You want to map them. You say, this is the I/O, this is my Ethernet, this is whatever, this board goes here, that board goes there. And the system takes care of creating and maintaining this separation. So here is the example that we are showing downstairs, and we are here tomorrow as well, and for the member of RISC-V on Thursday as well. So this is the real application. We have an FPGA that is running a Sci-5 core. In fact, we can run all of their cores that fit that FPGA. It was just fine. And we have on the attack exposed side, which can be an Ethernet, in this case is UART, because the Ethernet is not really mapped to that specific FPGA. That's the only reason. We have a dumb terminal that just interacts with the system. That's one zone. We have a third zone, which is one that controls the robotic arm. And the robotic arm, it's real time as it gets, right? It moves, it does things. It has to be exactly the real thing. You cannot fake it. And then we have a central zone that, in this case, is just flashing some LEDs and going through color patterns. But what's important is that that's the very same Sci-5 demo, which is called, I guess, the yellow word, that you get straight out of the Freedom ESDK. No changes. We just drop the executable there. It just works in its own contained environment. And if you want to know what happens there, you go downstairs and see a little bit of actions. We are showing these three robots. One is the micro semi boot, one is the Sci-5 boot, and the other one is the Antis boot. If you want to go on GitHub, that's where we open up under Apache to, this is free and it's open. So if you want to contribute to that, we're definitely looking for people who want to help us take this to the next level. And as I said, this is a commercial product, so we already announced some of our commercial agreements. There are more coming, very interesting, very soon. Okay? And with that, just to remind you a few points. Embedded systems, with or without MMU, and I would say any computing system to this extent, are intrinsically not secure. RISC-V gives you some of the building blocks, and I hope I show you some of those. But to just leave to every developer on the world to figure out how to put them together and make sure they work, security is that kind of thing. The bad guy takes one time to break in. The good guys need to get it right all the time, okay? That's better left to people who knows what they are doing, okay? So multi-zone is an example how you can get these all things together. There may be others coming up soon, and we welcome that. The security is provided by the hardware. This is a key concept. People ask me, so is this software or is it hardware? It's both. It's a software policy-driven enabler for some hardware hooks that are built into your ISA. And you already have them. It's okay to add more stuff, but sometimes in security, I would say most of the time, adding stuff doesn't make things more secure, just increases the attack surface. So think carefully about that. And the third point is that there's no real additional requirement either to change your code or to a very broad extent to change the hardware. With that, if we have 1 minute, I will take a question or two.
You talk about embedded, and you said that Linux is the next stuff. How do you handle virtual address?
Yes. So I guess the question is how this trust execution environment fits a rich operating system. It's a very easy way to explain it. So to the system that maintains separation, there's nothing special about Linux or about anything else. It's just a set of these definitions for the environment and one address to jump to start the execution. So Linux has nothing special. The important thing is that in the RISC-V implementations that we know, that runs in S mode. Yesterday, there was a very interesting presentation where people try to do without the S mode, which theoretically should be possible, but it's hard. It doesn't matter. So that's my answer to you.
Can you protect within the Linux?
Or is it just very good. That's another great question. So people familiar with the concept of enclaves, they know that Linux is so complex these days, people are actually trying to protect the user mode from the kernel itself. That's what happens. That's what happens. Privilege escalation is very common. It's just go on the CSV database and see how many are there, right? And with 70 million lines of code, that's what you would expect. So to your point, yes, it's possible. The way it's done is through a driver. So if you added, we're running out of time, but if you add a driver, you can get the user mode to actually access and communicate with this infrastructure. And depending on what you want to secure, you can have this privileged and secure communication in between your user mode, Linux user mode, through that driver. Now, whether you encrypt it or not, in an SoC probably you don't want to encrypt because it doesn't make a lot of sense. But if you have a platform kind of situation, that might be a situation. There are some interesting RISC-V cores coming up, Linux capable, integrated in silicon. And so you will see this running in some of those.